Now we're going to continue to look at derivative graphs and applications, and especially context, because again, it's great to be able to do the math, but it's important to be able to understand what you actually did, what it actually means, why you care about it, all of that fun stuff. This video is going to be much shorter than the last one. I do apologize, that one was kind of long, but I know you love to hear the sound of my voice, so you probably didn't even notice the time go by. Moving on. All right, the graph of a position function is shown below. That's a position function. It represents the distance in miles that a person drives during a 10-minute trip to work. Sketch the corresponding velocity function. Okay, so this is your position function of a 10-minute drive to work. You are going to sketch on the same graph what the velocity function would look like. So you need to think about, well, how does position relate to velocity? Great question. That's something we've already talked about, so you should know the answer to. All right, I want you to try to do this on your own. You can do it. Pause the video. Unpause when you're ready to check. All right, first thing, how does position relate to velocity? Well, the derivative of position is velocity, remember? So that means that we're looking for the derivative. What does the derivative represent? Great question. You should already know the answer because you do know the answer, and that is slope. So if I have the position function, all I have to do is identify the slope of that function. Since the position function is a linear function, I know the slope of the function. So this segment here has a slope of 5/6, and I can see that because I went up 5 over 6. So the derivative, or the velocity at that point, is going to be 5/6. So that is just a horizontal line at 5/6. Now this isn't perfect. Again, like don't worry if you're like, well, wait, how do I know that's 5/6 and not 7/8, right? Okay, it's 5/6. Trust me. Notice that I have open circles at the end because it's just undefined at those locations. And then here I jump down to 0. So the slope of this, I went up 0 over 2, so that's a slope of 0. So I'm just going to have a horizontal line segment at y equals 0. And then here again, I jump up to 1/2 because here I went up 1 over 2, so I have a horizontal line segment at y equals 1/2. So again, key takeaways. What do we want to know? We want to know the relationship between position and velocity. The relationship between position and velocity is the derivative. The derivative of position is velocity. What does derivative represent? Derivative represents slope. And one last thing to keep in mind is, so when we think about context, this was miles driven per minute. So when I see this velocity of 5/6, I might think to myself, that doesn't make a lot of sense as a velocity. But remember, that's miles per minute. This is not miles per hour. So it's miles per minute. So it actually is a realistic velocity. The next one. So the number of gallons N of gasoline sold by a gas station at a price of P dollars per gallon is given by N equals F of P. So I want you to describe the meaning of F prime of 1.479. And then I want you to think about, is F prime of 1.479 usually a positive or a negative number? And then explain why. So you're really going to have to think about this. Think about context. What does each variable represent? And then what does the derivative represent? Pause the video, unpause when you're ready to discuss this. Okay, so here we want to make sure we really understand the variables, like I was saying before I had you pause. And we understand that F of P is the number of gallons sold, where P is the price per gallon, price in dollars of a gallon. So when we want to think about, well, what is the meaning of F prime of 1.479? Well, first we need to think about what is the meaning of F prime of P. So the derivative of the function is going to be the rate in change of the number of gallons sold at a given price P. Remember, a derivative is just a rate of change. It's the slope, right? So F prime of 1.479 is the rate of change of the number of gallons sold when the price is $1 and $1.479 per gallon. And don't think this is weird, because if you go to a gas station, they have 3 decimal places, and it always ends in 9. So think about this as saying how the number of gallons sold is changing based on the price. Now, the next part, and this part might be a little bit more difficult to think about. So is F prime of 1.479 usually positive or negative? Now, the first thing I would argue is I would say, well, If gas is at $1.479 per gallon, people are probably buying more gas because it's really cheap. That would be really cheap for gas. However, if we think about, so then that might lead you to believe, well, then it would be positive. But if we think about what does this actual function look like, well, the function, the input to the function is price and the output is number of gallons sold. So if I think about that function, as price increases, the number of gallons sold is typically going to decrease. So this is not exactly what the function might look like, but something like this, right? Where this is price, this is gallons. So as price is increasing, the number of gallons is probably going to decrease because again, in this case, people, or just in general, people usually buy less gas if it's more expensive. You know, they try to conserve a little bit, drive a little bit less if they can, depending on how much more expensive we're talking about, right? Whether it's an actual function like this, whether it's linear, whether it's something else, I don't know. But the point is that this sort of general idea of as the price goes up per gallon, the number of gallons sold is going to decrease. That should make sense. Therefore, f prime of 1.479 is usually negative because it's representing the slope, and this is going to have a negative slope. So this is assuming that f of p, so this is my explanation. This is assuming that f of p is a decreasing function where the number of gallons sold decreases as price goes up or as price increases. Boom. I know, that was the sound of your mind being blown. But you got it. Last example is already, I know, you love to sketch graphs of functions and derivatives and their relationship. So given the graph of g prime, so this is the derivative of g, we want to sketch the graph of g. You've done this before, we've done this many times. We have done this very beginning of this unit. It's something that some of you really enjoyed, some of you didn't, but it really helps you have a better understanding of derivatives. Remember that there are actually multiple correct answers. So I want you to pause the video and do this on your own. Feel free to look back at your notes or your other examples that you've done before of this, or just try it. Don't cheat though. Nobody likes a cheater. Pause the video. Unpause when you're ready to check. All right, so anyone have an idea on where I came up with this? Okay, guess not. I guess I'll just do the talking this time then. All right, so this is my graph of G. Remember, it doesn't have to be that. It could be some vertical translation of this. These points, I don't know exactly how high or low they are. That doesn't matter. What I do know, though, is at -3, at -1, and at 1, the function had to have a slope of 0, so there have to be relative minimums and maximums at those points. Okay, this is a little bit off. There we go. A little bit better. And I know that because the derivative was 0 at those points. Now, how do I know that -3 is a minimum versus a maximum? Great question. But remember, the derivative represents slope. So if the slope is negative, then the slope is 0, and then the slope is positive, that means the function had to be decreasing, have a relative minimum, and then increase. Here, the slope is positive because the y coordinates are positive. Remember, that's what I'm saying. When I say the slope is positive, I'm not saying the slope of this function is positive. I'm saying the values, the y coordinates here are positive, then the y coordinates are 0, then the y coordinates are negative. So that means the slope of the function had to be positive, 0, and then negative. Here the y coordinates are negative, 0, and then positive. Therefore, the slope was negative or decreasing, 0, and then positive. So I know it has to be something like this. And again, and it has to have this end behavior as well, because that's how I can create these relative minimums and maximums. But again, vertically where this is, I don't know that. Okay, conclusion, average rate of change is change in distance over change in time. That's just our regular slope. Instantaneous rate of change is the derivative at a point. The derivative of the position function is velocity. That is our instantaneous rate of change. The derivative of velocity is acceleration. The second derivative of position is the derivative of velocity, which is acceleration. Think about units and inputs versus outputs to really help you understand context of functions. Nice work.